strangest force in the universe is not a black hole, not a supernova, and not some distant monster hiding in the dark. It is empty space itself. Right now, all across the cosmos, the universe is expanding faster and faster, as if something woven into the vacuum is quietly pushing everything apart. That idea changes almost everything. By the end of this journey, you will understand what dark energy is supposed to be, why scientists take it seriously, how we discovered it, why it may decide the ultimate fate of every galaxy, star, planet, and atom we know, and why one of the biggest things in reality might also be one of the least understood. And if you genuinely enjoy this kind of deep space storytelling, take a second to like the video and subscribe. It really does help, and it tells me you want more journeys like this. And while you are here, leave a comment saying where you are watching from, and tell me this: when you imagine the end of the universe, do you picture darkness, cold, fire, or something even stranger? Now, let us step into one of the most unsettling discoveries modern science has ever made. Imagine looking out across the night sky, thinking gravity should be pulling the universe together, only to find that the exact opposite seems to be happening. What could possibly overpower gravity on the scale of the entire cosmos? How can nothing, the vacuum of space, behave like something with real physical effects? If dark energy is real, what is it actually made of, if anything at all? And if it keeps winning, what kind of future is waiting for the universe? To understand dark energy, we need to begin with a simpler picture of the universe than the one we have now. For most of human history, the cosmos seemed fixed. The stars rose and set. The planets wandered. The Milky Way arched overhead like a permanent river of light. The universe looked eternal and stable, even if its details were mysterious. Then the 20th century arrived and shattered that old idea. Einstein gave us general relativity, a new description of gravity that was not really about invisible forces reaching across empty space. Instead, gravity became geometry. Matter and energy tell space-time how to curve, and curved space-time tells matter how to move. A planet orbits a star not because it is being yanked by an invisible rope, but because it is following the natural curves in the structure of space-time around that star. This picture was elegant, now powerful, and strange enough on its own. But when Einstein applied his equations to the entire universe, he found something awkward. The equations seemed to say that the universe could not simply sit there unchanged. It should either expand or contract. Einstein, like many scientists of his time, believed the universe was static, so he adjusted the equations by adding an extra term, a kind of cosmic balancing factor now called the cosmological constant. That addition could, in principle, hold the universe up against collapse. Then came the observations that changed everything again. In the 1920s, Edwin Hubble and others found that distant galaxies were moving away from us, and the farther away they were, the faster they seemed to recede. The universe was not static. Space itself was expanding, and galaxies were not flying through a pre-existing void like shrapnel through air. The fabric of cosmic distance was stretching. That distinction matters. It is one of the keys to understanding dark energy. If the universe expands, it does not necessarily mean Earth is at the center. and it does not mean every galaxy is blasting outward from some central explosion point into emptiness. A better image is dots on the surface of an inflating balloon. As the balloon expands, every dot sees every other dot moving away. The farther apart two dots are, the faster the distance between them grows. Not because the dots are crawling across the rubber, but because the rubber itself is stretching. Space, on the largest scales, behaves more like that balloon than like a fixed stage. Now, if gravity is an attractive effect, and if the universe began in a hot, undense early state, then a natural question follows. Expansion, yes? But what kind of expansion? Common sense suggested that gravity should gradually slow it down. The universe might expand forever, but more and more sluggishly. Or if there were enough matter, gravity might eventually halt the expansion and reverse it, leading to a future collapse, sometimes called the Big Crunch. For decades, that was the basic argument. The key uncertainty was not whether gravity would oppose expansion. Of course it would. The uncertainty was how much matter the universe contained, and therefore how strongly the cosmic brakes were being applied. Scientists spent years trying to weigh the universe. They counted galaxies, studied clusters of galaxies, measured motions, and soon ran into another mystery. There was not enough visible matter to explain what gravity seemed to be doing. Galaxies rotated too fast. Clusters held together too strongly. Something unseen appeared to contribute extra mass. That invisible component became known as dark matter. Dark matter and dark energy are often mentioned together, but they are not the same thing. Dark matter seems to pull through gravity. It helps build cosmic structure, acting like hidden scaffolding that galaxies form around. Dark energy, by contrast, appears to do something much stranger. It acts on the largest scales as if it is driving accelerated expansion. Dark matter helps hold the universe together locally. Dark energy helps pull the large-scale universe apart. One adds gravitational glue. The other behaves more like cosmic anti-gravity, though even that phrase can be misleading if taken too literally. For a while, the expectation remained that once astronomers measured enough of the universe, they would determine whether expansion would coast to a crawl, continue forever, or eventually reverse. Then, in the late 1990s, two teams observing distant exploding stars found something deeply surprising. These stars were a special kind called Type 1a supernovae. They are useful because they can serve as standard candles, objects with a known intrinsic brightness. If you know how bright something truly is, and compare that to how bright it appears from Earth, you can estimate how far away it is. It is like seeing two identical flashlights at night. If one looks dimmer, it is probably farther away. Real astronomy is more careful than that, but the basic idea holds. These supernovae are incredibly bright enough to be seen across huge cosmic distances. That makes them powerful tools for studying the expansion history of the universe. The logic was simple. If the expansion had been slowing over time, then distant supernovae, whose light left them billions of years ago, should line up with one pattern. If expansion was behaving differently, the pattern would change. And the pattern did change. The distant supernovae appeared dimmer than expected. The simplest interpretation was that they were farther away than they should have been if cosmic expansion had been slowing down under gravity alone. In other words, the universe was not just expanding, it was accelerating. This was astonishing because it implied that, on the largest scales, gravity was not in control by itself. Something else was pushing the expansion to speed up. This is the moment when dark energy enters the story. The name is both useful and frustrating. Useful because it labels a real mystery in cosmology. Frustrating because it can sound as if scientists have found a dark, glowing substance floating through space and simply chosen not to tell anyone what it is. That is not what is going on. Dark here mostly means unseen and unknown. Energy points to the fact that whatever this is, it behaves in the equations like a form of energy associated with space itself, or with a field-filling space, or with some modification of gravity that mimics such an effect. So, what is dark energy? The most honest answer is this: we do not know exactly, but we do know why scientists think something like it is needed. When cosmologists map the universe with multiple independent methods, the same broad picture keeps appearing. Measurements of the cosmic microwave background, the afterglow of the early universe, the large-scale distribution of galaxies, and the supernova evidence all point toward a universe in which ordinary matter makes up only a small fraction of the cosmic budget. Dark matter contributes more, and the largest share seems to belong to dark energy, around roughly 2/3 to 70%, depending on the model and dataset used. The exact values are refined over time, but the main conclusion remains. Most of the universe, in terms of its energy content, does not consist of stars, planets, gas, dust, or any familiar material. You, the Earth, the Sun, every glowing nebula, every black hole formed from dead stars, every visible galaxy in every telescope image, all of it belongs to a minority component of reality. That alone is humbling. But the deeper shock is not just that dark energy dominates the cosmic budget. It is that it appears to dominate the future. To see why, imagine the universe as a contest between different influences. Matter, whether ordinary or dark, tends to slow expansion because gravity attracts. Radiation also contributes energy. But in the early universe, it mattered much more than it does now. Dark energy, if it behaves like a property of space itself, does something different. As the universe expands, matter gets diluted. The same amount of matter spreads through a larger volume. Its average density drops. Radiation thins out even faster because not only does its density drop, but each photon also gets stretched to longer wavelengths and lower energy as space expands. Dark energy does not necessarily fade the same way. If dark energy is the cosmological constant, then it is simply the energy density of empty space, and that density stays constant even as space expands. That sounds innocent until you think through the consequence. If each cubic region of space carries the same vacuum energy, then as the universe gets larger and creates more cubic regions of space, the total amount of dark energy effectively increases with volume. Space expands, and there is more space. More space means more vacuum energy, and more vacuum energy drives more accelerated expansion. At first, in the early universe, matter was dense, and gravity had the upper hand. Galaxies formed, clusters formed, structure emerged. dark energy, if it was present then in this cosmological constant form, would have been comparatively unimportant because matter density was so much higher. But as the universe expanded for billions of years, matter thinned out. Dark energy, not thinning the same way, eventually became dominant. Once it did, the expansion began to accelerate. This is one of the most important conceptual turns in all of cosmology. The universe is not accelerating because galaxies are somehow pushing off one another. It is not because there was a bigger bang than expected. It is because the large-scale behavior of space-time seems to include a component that makes expansion accelerate naturally. Now let us make that idea less abstract. Suppose you had a huge loaf of raisin bread dough rising in the oven. The raisins are galaxies. As the dough expands, every raisin sees other raisins moving away. If the dough were rising but slowing down, the distances would still increase, just more gently over time. But dark energy is like discovering that the dough is not merely rising. The expansion of the dough itself is increasingly favored by the underlying physics. The farther apart distant raisins are, the more dramatic that added separation becomes. On local scales, gravity or other forces can still hold things together. The raisins themselves do not swell apart because the dough rises. But on large enough scales, the space between them grows faster and faster. This is where an important caution comes in. Dark energy does not make your body expand. It does not tear the solar system apart under the standard cosmological constant picture. It does not unbind the Milky Way or even the local group of galaxies that are already gravitationally bound, at least not in the ordinary dark energy scenario. Local structures held together strongly enough by gravity, electromagnetism, or nuclear forces resist the expansion of the universe. Cosmic expansion matters mainly across vast distances between systems not strongly bound to one another. That distinction helps answer a common question. If space is expanding everywhere, why do not atoms, planets, and galaxies all inflate? Because the effect of cosmic expansion on small bound systems is tiny compared with the forces holding them together. The universe can expand globally, while neighborhoods with strong local binding remain effectively intact. It is a little like a continent drifting apart from another continent, while the rocks in your backyard stay right where they are. The analogy is imperfect, but the key point is scale. So dark energy governs the fate of the universe, not because it immediately destroys local structures, but because over immense stretches of space and over immense spans of time, it shapes the overall trajectory of cosmic history. That raises another question. If dark energy is the energy of empty space, where does that idea come from? Part of the answer lies in quantum physics. In quantum field theory, empty space is not truly empty in the classical sense. The vacuum is not a bland, featureless void. It seethes with fields, fluctuations, and temporary quantum activity. Particles and antiparticles can briefly appear and disappear in ways that do not violate the deeper rules of quantum mechanics. This is often described, a bit poetically, as the vacuum bubbling with virtual particles. That sounds like exactly the sort of place you might look for an energy built into empty space itself. And indeed, physicists can calculate vacuum energy contributions in quantum field theory. But then we run into one of the biggest train wrecks between theory and observation in modern science. The predicted vacuum energy from naive quantum calculations is absurdly large compared with the tiny value needed to match the observed cosmic acceleration. Not a little large, not our estimate is off by a factor of 2. Depending on how the estimate is framed, the mismatch is often described as the worst theoretical prediction in physics, off by an almost incomprehensible amount. It is the kind of discrepancy that makes scientists deeply uncomfortable, because it suggests either that our understanding is incomplete in a major way, or that delicate cancellations we do not yet understand are taking place, or that we are asking the question incorrectly. This is known as the cosmological constant problem, and it is one reason dark energy is not just another box checked in an astronomy textbook. It is a crack in our picture of reality. If the cosmological constant is the right explanation, then we still do not know why it has the value it does. Why is vacuum energy not vastly bigger? Why is it not zero? Why does it seem to become important around the era in cosmic history when complex structures and observers exist? That last puzzle is sometimes called the coincidence problem. Why now? Why do we happen to live in the era when matter and dark energy are of the same general order of importance, even though they evolve differently over time? In cosmic terms, that could be a fleeting phase. Some scientists view that as a clue. Others think it may simply reflect selection effects or deeper underlying physics we have not uncovered yet. But either way, it is not a trivial detail. The value of dark energy determines the universe's large-scale destiny. If it had been much larger earlier on, matter might never have clumped into galaxies. Stars might never have formed. Planets, chemistry, biology, once, and us might never have had a chance. That does not mean dark energy was somehow designed for life. It means the universe appears to occupy a narrow and puzzling range of conditions in which complexity became possible. Why that is true remains an open question, and the scientific conversation around it ranges from hard calculations to very careful philosophical discomfort. Now, the cosmological constant is the simplest model, and in science, simple models matter because they are testable and often surprisingly successful. In the standard cosmological model, usually called lambda CDM, the lambda stands for the cosmological constant, and CDM stands for cold dark matter. This framework does a remarkably good job describing many observations of the universe, and from the large-scale web of galaxies to the pattern of tiny temperature fluctuations in the cosmic microwave background. If you want the short version, the standard model says this: the universe began hot, dense, and expanding. Matter and radiation shaped the early phases. Dark matter helped seed and build structure. And in the later universe, dark energy, represented as a cosmological constant, came to dominate the large-scale expansion and accelerate it. It is powerful. It is elegant in a certain stripped-down way, but it may not be the whole story. Because once you realize we are inferring dark energy from how the universe expands, another possibility appears. Maybe there is no mysterious energy component at all. Maybe general relativity itself needs to be modified on the largest scales. Maybe gravity behaves slightly differently across cosmic distances than Einstein's equations predict in their simplest form. If so, what looks like dark energy could really be a sign that our theory of gravity is incomplete. This is not scientific rebellion for its own sake. It is a legitimate response to a deep mystery. If the data tell us the universe accelerates, we have at least two broad families of explanation. One says there is an extra component in the universe causing this behavior. The other says our equations for gravity need revision. There are hybrid ideas, too, along with more exotic proposals. Some dark energy models involve a dynamic field rather than a true constant. One famous category is called Quintessence. In these models, dark energy is not fixed vacuum energy, but a field that can evolve over time and changing how strongly it affects cosmic expansion. That difference matters because it could alter the future of the universe and leave subtle signatures in observations. If dark energy changes with time, then the history of expansion may deviate from the simple cosmological constant picture. Scientists often describe the behavior of dark energy using something called the equation of state parameter, usually written as W. You do not need the math details here. What matters is the idea behind it. This parameter tells us how pressure relates to energy density. For an ordinary cosmological constant, W equals -1. That negative pressure is the crucial part. In general relativity, pressure contributes to gravity just as energy density does. A sufficiently negative pressure can lead to accelerated expansion. This is one of those moments where the universe becomes wonderfully counterintuitive. We are used to pressure meaning something that pushes outward, like air in a tire. In cosmology, negative pressure is not a simple, everyday push. It is a property in the stress-energy content of space-time that affects how expansion evolves. If a component of the universe has the right kind of negative pressure, it can make the expansion accelerate. If W is exactly -1, the cosmological constant picture remains in excellent shape. If future measurements find W differs from -1 or changes over time, that would be a huge clue that dark energy is something more dynamic. So far, observations are broadly consistent with -1 within uncertainties. That means the simplest explanation is still standing. But still standing is not the same as fully understood. And this is where modern cosmology becomes a kind of precision detective story. Scientists are not just looking for dark energy in one dramatic image. They are measuring its fingerprints across multiple cosmic records. They use supernovae to map distances and expansion history. They study the cosmic microwave background, relic light from about 380,000 years after the Big Bang, because its subtle patterns encode the geometry and contents of the universe. They track baryon acoustic oscillations, faint ripples in the large-scale distribution of galaxies left behind by pressure waves in the early universe. These ripples act like a standard ruler imprinted across space, letting astronomers compare cosmic distances at different times. They also examine weak gravitational lensing, where the gravity of matter bends light from distant galaxies, because the growth of structure and the geometry of the universe both depend on the underlying cosmological model. These methods are not all measuring the same thing in the same way. That is what makes the agreement among many of them so compelling. When independent tools point toward accelerated expansion and a dark energy-like component, confidence grows that we are seeing something real. At the same time, cosmology is not a finished puzzle. There are tensions in the data, places where different measurements do not line up as comfortably as we would like. One of the best known is the Hubble tension, the disagreement between different methods of measuring the present-day expansion rate of the universe. And some methods based on the early universe and the standard cosmological model give one value. Other methods based on more local measurements give a somewhat higher value. This does not automatically mean dark energy is wrong. It does not automatically mean a revolution is coming either. It could reflect subtle systematic errors. It could point to new physics. It could involve modifications to our understanding of the early universe, dark energy, or something else entirely. But it is another sign that cosmology remains alive, unsettled, and open. That is worth emphasizing. Dark energy is not one mystery isolated from all others. It sits at the center of a web of profound questions. What is the vacuum? How should quantum physics and gravity fit together? Why does the universe have the large-scale properties it does? Is general relativity complete across all scales? And what determines the long-term fate of cosmic structure? Let us talk about that fate directly, because this is where dark energy stops being an abstract parameter and becomes the author of endings. If dark energy is a cosmological constant, and if it remains constant forever, the universe will continue expanding at an accelerated rate. Not in the sense that every individual galaxy keeps speeding through space in some explosive way, but in the sense that distances on large scales grow more and more rapidly. Over enough time, distant galaxies outside our local gravitationally bound group will move beyond our cosmic event horizon. That phrase sounds dramatic, but the idea is subtle and real. Because expansion can accelerate, there are regions of the universe whose light, emitted in the future, suns, will never reach us. Not because they are moving through space faster than light in a forbidden way, but because the space between us and them expands so quickly that the light can never make net progress across the gap. General relativity allows space itself to expand in this way, without violating the local speed limit set by special relativity. The consequence is eerie. In the unimaginably far future, observers in our cosmic neighborhood may see a much emptier sky than we do. Galaxies not gravitationally bound to us will fade from view. The large-scale universe beyond the local group will become effectively inaccessible. The cosmic microwave background will be stretched to such long wavelengths that it becomes extremely difficult, perhaps practically impossible, to detect. The evidence for the Big Bang itself may eventually disappear from easy observation. Imagine that. Future astronomers, if any exist trillions of years from now, in a long-lived gravitationally bound remnant, may look out and see a lonely island universe, with little sign that countless galaxies once filled the sky. We happen to live at a time when the universe is old enough for complex structure to exist, and young enough that the great cosmic story is still visible. Dark energy makes our era unusually informative. But that is only one future, the standard one. If dark energy is dynamic, the ending could be different. Suppose dark energy gradually weakens over time. Then acceleration might slow. Depending on the details, the universe could still expand forever. But the long-term picture would differ from the neat, exponential-like expansion associated with a pure cosmological constant. In some models, dark energy could even change sign or behavior, potentially allowing a future recollapse, though present evidence does not favor that. Then there is the more dramatic possibility known as phantom energy, a hypothetical form of dark energy with an equation of state parameter less than -1. If that sounds like a tiny mathematical distinction, its consequences are anything but tiny. In such models, the energy density of dark energy increases as the universe expands. The acceleration becomes ever more violent. Eventually, the expansion does not merely isolate galaxy clusters. It can overpower the gravity holding galaxies together, then the forces holding solar systems together, then planets, then molecules, then atoms. This hypothetical end is called the Big Rip. If the Big Rip scenario were correct, the timeline would unfold in stages. Billions of years before the final moment, galaxy clusters would disperse. Closer to the end, galaxies themselves would be torn apart. Still later, planetary systems would be disrupted. In the final instance, even atomic structure could fail as space-time expansion became catastrophically dominant on all scales. It is one of the most vivid and disturbing endings ever proposed in cosmology. But it is important to be careful here. The Big Rip is not the leading prediction under current evidence. Observations are broadly consistent with dark energy behaving like a cosmological constant, not clearly like phantom energy. The Big Rip remains a scientifically interesting possibility and not a present best bet. Even so, the fact that small differences in dark energy's behavior can determine whether the universe ends in quiet isolation, slow thermal exhaustion, future collapse, or catastrophic tearing, gives you a sense of why this subject matters so much. Dark energy is not some optional decoration on the edge of cosmology. It is central to the ultimate script of cosmic time. Now let us zoom back toward the present and ask a harder question. If dark energy dominates the energy budget of the universe, why do we not detect it directly in laboratories? Partly because dark energy, as inferred from cosmology, is incredibly diffuse. Its effects are tiny on local scales. Across a room, a city, the solar system, even a galaxy, ordinary forces and local gravity dominate. And dark energy reveals itself only when you look across vast cosmic distances and over long times, where cumulative effects become measurable. It is like trying to detect the slope of Earth's curvature by staring at your kitchen floor. The effect is real, but your setting is too small. There is another issue, too. Theoretical ideas about vacuum energy are tied to deep physics, but connecting those ideas cleanly to experiments is hard. Dark energy may be a feature of space-time itself, not a substance we can bottle. Or it may come from a field that couples so weakly to normal matter that its influence is almost impossible to isolate, except through cosmic expansion. This is one reason the mystery persists. The universe shows us the effect in its largest behavior, but the mechanism hides behind layers of theory and scale. And yet scientists keep pushing. Major surveys map millions of galaxies to reconstruct the history of expansion and the growth of structure. Space telescopes and ground observatories refine supernova measurements. Instruments study weak lensing to see how matter bends light over cosmic time. Missions are designed not to photograph dark energy in any simple sense, but to constrain its properties with enough precision that some models survive and others fail. This is how science often advances when it reaches something fundamental, not with one dramatic reveal, but by tightening the net. The search for dark energy also changes how we think about emptiness. For most of ordinary experience, Empty space seems like the absence of things, a blank, a stage with nothing on it. And physics has spent the last century destroying that intuition piece by piece. First, relativity told us space and time are dynamic, flexible, woven together. Then quantum theory told us the vacuum is not inert. Then cosmology told us the geometry and content of the universe evolve. Dark energy pushes that transformation further. Empty space may possess an energy that shapes the fate of the cosmos itself. That is an extraordinary sentence. Empty space may determine everything. But to appreciate the full force of that statement, we need to be precise about what control means here. Dark energy does not micromanage every event. It does not decide whether a star forms in a particular cloud or whether a planet survives a nearby supernova. Local physics remains rich, violent, and varied. And what dark energy controls is the long-range framework within which all those local stories unfold. It controls whether the large-scale universe expands gently, accelerates forever, recollapses, or ends in more exotic ways. It controls how isolated future structures become. It controls how much of the observable universe remains observable in the deep future. It sets the background against which all cosmic histories play out. In that sense, dark energy is like the slowest and largest force in the story, but also the one with the final word. There is a haunting beauty in that. The stars feel powerful. Black holes feel powerful. Supernovae feel powerful. But those are episodes within galaxies, within clusters, within an expanding universe. Dark energy operates at the scale of the stage itself. It is not the loudest actor. It is the one moving the walls. The more you think about it, the stranger it becomes. Take a galaxy billions of light years away. Its stars live and die. Planets form. Heavy elements are forged. Maybe life emerges somewhere in its spiral arms. Yet across the gulf, the metric of space between that galaxy and ours is stretching under a rule tied, perhaps, to vacuum energy. If enough time passes, the galaxy may cross beyond the horizon of possible future contact. Not because anything exploded, not because anyone chose a direction, but because the large-scale architecture of reality favors increasing separation. Dark energy turns distance into destiny. And if that sounds abstract, consider what it means for observation itself. Astronomy is usually an act of recovery. Light travels for years, centuries, millions of years, billions of years, on carrying history to us. The night sky is a museum of delayed messages. But in an accelerating universe, some future messages will never arrive. Some parts of the universe are not merely far away. They are becoming permanently unreachable. There are events happening right now beyond a threshold from which no future light signal, emitted after a certain point, will ever get here. The universe is not just vast. It is selectively becoming more alone. Still, even within that loneliness, structure can survive for astonishing spans of time. Our local group, containing the Milky Way, Andromeda, and smaller galaxies, is gravitationally bound strongly enough that cosmic expansion does not pull it apart under the standard picture. In several billion years, the Milky Way and Andromeda are expected to merge. The merged remnant, along with associated bound systems, may become an island universe adrift in expanding darkness, while more distant galaxies vanish beyond reach. There is something almost poetic about that image. Not comforting exactly, but vivid. A future cosmic civilization, if one ever exists in such an era, might inhabit a bound remnant of galaxies surrounded by a sky stripped of evidence. Cosmology itself could become harder, perhaps impossible, because dark energy would have hidden the wider universe. That possibility gives our present era a special kind of intellectual privilege. We can still see the cosmic microwave background. We can still measure distant galaxies in every direction. We can still infer large-scale expansion from a rich, visible sample. We are not at the beginning of cosmic time, but we may be living in a period unusually favorable for understanding the universe's history, and that has a subtle emotional weight. The universe is not just strange, it is time-sensitive in what it allows observers to know. Now, there is another layer to this mystery, and it is one that often gets less attention in popular discussions. Dark energy may force us to rethink not only what the universe contains, but how explanation itself works in cosmology. When science succeeds, we often get used to a certain style of answer. What is light? Electromagnetic radiation. What are stars? Self-gravitating balls of hot plasma powered by nuclear fusion. What causes tides? Primarily, the gravitational pull of the moon, and to a lesser extent, the sun. These answers can be deepened, refined, mathematized, and challenged, but they have a satisfying explanatory shape. Dark energy is not there yet. At present, our best explanations often sound more like this. Observations show the expansion is accelerating. The simplest model that fits many datasets includes a cosmological constant. Other possibilities remain under investigation. The underlying physical origin is unknown. That is honest science. It is also a reminder that being able to describe a phenomenon precisely is not the same as fully understanding why reality works that way. In some sense, dark energy lives in that gap between measurement and meaning. And this is not a failure. It is where frontier science actually happens. The public image of science can sometimes make it seem like knowledge advances by clean, complete replacements of ignorance with certainty. Real science is messier and more impressive than that. It advances by building reliable islands of understanding surrounded by open water. Dark energy is one of the largest open waters we know. The story also reveals something profound about the relationship between the tiny and the enormous. The behavior of the whole universe may depend on quantum properties of the vacuum, on the structure of space-time, on gravity, on fields, on symmetries and symmetry breaking, on the physics of the very early universe, perhaps even on inflation or deeper frameworks still under development. The largest thing we can study may be controlled by the smallest ingredients in our theories, and by the tension between those theories. That is one reason cosmology matters beyond simple curiosity. When we ask what dark energy is, we are not merely asking about the future of galaxies. We are probing the foundations of physics. If we solve dark energy, we may learn something essential about vacuum energy, quantum gravity, the architecture of field theory, or the limits of general relativity. The mystery reaches downward as much as outward. Of course, there is always the possibility that the eventual answer turns out to be disappointingly plain from a storytelling perspective. The cosmological constant may simply be a basic property of nature with a value we measure rather than derive elegantly. The universe does not owe us dramatic mechanisms. It does not care whether our preferred answer feels satisfying. Sometimes reality is stranger than fiction, precisely because it resists narrative neatness. But even that would be extraordinary. To discover that empty space has a tiny, intrinsic energy density that dominates the fate of the cosmos is not a boring answer. It is an answer so strange that we risk becoming numb to it, only because we repeat the words too often. So let us pause and really look at it. You are living in a universe where the vacuum may outweigh the stars, where the great web of galaxies, glittering and violent as it is, may be a temporary phase in a larger story of accelerating emptiness, where the darkness between galaxies is not just a gap, but possibly the most influential thing in the cosmos, where the future sky of any distant civilization may steadily lose galaxies, not because they die, but because the geometry of space carries them away forever. This is not science fiction. It is the current frontier of physical cosmology. There are, naturally, skeptics and alternative approaches. Good science needs them. Some researchers examine whether inhomogeneities in the universe, the uneven distribution of matter, could mimic the appearance of acceleration when averaged over large scales. Others develop modified gravity models and test whether they can reproduce observed expansion and structure growth without invoking a separate dark energy component. These ideas face strong constraints, and many simple alternatives struggle against the data. But the investigation is important because it prevents cosmology from becoming complacent. The burden of proof in science is not to prefer the weirdest idea, or the simplest phrase, or the most dramatic end state. It is to follow the evidence and see which framework survives precision tests. At the moment, dark energy, in the form of a cosmological constant, remains the benchmark because it works remarkably well. Yet the fact that it works does not erase the conceptual mystery of why it exists and why it has the value it appears to have. And that brings us to an unsettling truth. Dark energy is both one of the most successful ideas in cosmology and one of the least satisfying in fundamental physics. That tension is part of its power. It is not merely a missing ingredient. It is a signpost pointing beyond our current understanding. Think about how many times science has encountered something first as an effect before understanding its source. Planets moved in strange ways before gravity was formally described. Spectral lines were measured before quantum mechanics explained atomic structure. The expansion of the universe was observed before cosmologists knew about dark energy. Often, the universe lets us see what happens long before it tells us why. We may be in that stage now, and if so, future generations may look back on our current term, dark energy, the way we look back on older scientific placeholders. A useful label for a real phenomenon, waiting for deeper theory. Or they may find that the cosmological constant was the final answer after all, and that the true challenge was not naming the effect, but accepting what nature had already shown us. Either way, the lesson is humbling. The visible universe fooled us. We looked at stars and assumed they were the main event. We discovered dark matter and learned that much of the mass is invisible. Yes, we discovered accelerated expansion and learned that the long-term behavior of the cosmos may be governed by something even more elusive. Every time we widen the frame, the familiar shrinks. Now let us return to the raw physical picture one more time and make it intuitive. Picture the universe in its early eras, dense and hot, matter packed far more closely than it is now. Gravity pulls, clumps, and amplifies tiny irregularities. The first stars ignite. Galaxies gather. The cosmic web grows like luminous frost across a dark window. During all of this, matter is doing what matter does. It dominates because it is dense. The universe expands, yes, but structure still wins locally and widely. Then, slowly, the balance changes. Not because matter disappears, but because expansion spreads it thin. Dark energy, if constant, does not dilute in the same way. It becomes relatively more important simply by staying the same while everything else thins out. Eventually, it takes over the large-scale evolution. From then on, the universe enters a new chapter, one in which the distances between unbound structures grow faster and faster. Nothing explodes at that moment. There is no cosmic alarm, no visible wall of force sweeping through space. A galaxy on its own does not look up and notice a change in the sky overnight. The transition happens over billions of years. But on the scale of the universe, it is a turning point as real as the formation of the first atoms or the ignition of the first stars. The age of matter gives way to the age of dark energy. We are living inside that transition. That may be the most astonishing part of all. This is not a remote event buried in the first fractions of a second after the Big Bang, accessible only through abstract equations. It is the era we inhabit. The universe around us is currently being shaped on the largest scales by a component we cannot see and do not understand. We are not outside the mystery looking in. We are inside it. And what does that mean for the very far future if the standard model holds? Stars will continue to form for a while, though star formation is already declining compared with the cosmic past. Existing stars will age and die. Galaxies in bound systems will merge. Black holes will persist for incomprehensible lengths of time. On the grandest scales, though, accelerated expansion will continue to dilute the wider cosmos into isolation. Energy sources will diminish. The universe will trend toward a colder and a darker, more diffuse state, often called heat death, though that phrase covers many staggeringly long processes. Dark energy does not cause heat death by itself, but it strongly shapes the road to it by ensuring that large-scale separation keeps increasing and that the observable universe becomes more fragmented into isolated islands. This is the quiet ending. No final flash, no curtain of fire, no dramatic collapse. Just an ever faster widening, a thinning of contact, a dimming of accessible structure. It is cosmic exile by geometry. And still, even this bleak vision has grandeur. The universe does not owe us a human-style ending. Its future may be less like a story climax and more like a tide going out forever. Of course, every one of these long-term futures depends on what dark energy really is. If it changes, the script changes. Or if gravity behaves differently than we think, the script changes. If the standard model needs revision, the script changes. That uncertainty is not a weakness in the narrative. It is the narrative. The fate of the cosmos hangs on a quantity whose origin remains obscure. Few scientific questions are so vast and so direct at the same time. What is dark energy? Why does empty space have the properties it does? Will cosmic acceleration continue forever? And what kind of universe are we actually living in? These are not decorative questions around the edge of astronomy. They are central to the nature of reality. There is also an emotional reason dark energy resonates so deeply. It takes one of the oldest human symbols, the void, and turns it into an active presence. For most of history, darkness meant ignorance, absence, maybe danger. In modern cosmology, darkness has become architecture. Dark matter shapes galaxies. Dark energy shapes the destiny of space itself. The unseen is not just what we have failed to light up. It is what makes the visible world possible and temporary. That can feel disorienting. It should. A good cosmological idea often does not flatter human intuition. It stretches it. The universe is under no obligation to be built out of only the things our senses evolved to notice on one small planet around one ordinary star. And this is where the awe comes in, not as decoration, but as a consequence of understanding. Once you truly grasp the idea, the night sky changes. You still see stars. You still see the calm glow of the moon and the spray of the Milky Way. But behind that familiar beauty lies a larger truth. The visible heavens are only the bright surface of a deeper cosmic structure, ruled in part by something hidden, quiet, and immense. The fate of everything may depend on what empty space is. That sentence would have sounded absurd not long ago. Now it sits near the center of serious physics. What dark energy reveals more than anything is how incomplete our confidence should be when the universe appears simple. The sky looks peaceful. The galaxies look like islands. Space looks empty. But the deeper we investigate, the more reality slips out from under ordinary intuition. Space is dynamic. Time is relative. Matter is mostly invisible. And emptiness may be the dominant actor of all. There is a kind of maturity in accepting that, without trying to force it into a comfortable shape. We do not need the universe to become smaller, friendlier, or more familiar to appreciate it. In fact, its refusal to do so is part of what makes science powerful. Each good observation strips away a convenient illusion and replaces it with something truer, stranger, and often more beautiful. Dark energy may eventually be explained by a future synthesis of quantum physics and gravity. It may turn out to be vacuum energy, after all, with a deeper reason for its tiny value. It may reflect a new field, a modified theory of gravity, or some framework we have not yet imagined. Whatever the answer, the process of confronting it is already teaching us something essential. Our best map of the cosmos is still incomplete, and the missing parts are not minor details. They are the terms that decide the ending. So when scientists say dark energy controls the fate of everything, they do not mean it reaches into your living room and steers your coffee cup across the table. They mean that on the largest scales, over the longest times, dark energy appears to govern whether the universe becomes more connected or more isolated, whether expansion slows or accelerates, whether the night sky remains populated or empties into loneliness, whether cosmic structure has an endless stage or a vanishing audience. It controls the direction of the whole. And perhaps the most astonishing part is that we discovered this not by leaving the solar system, not by drilling into some hidden layer of space, but by patiently measuring faint points of light, by comparing brightness and distance, by reading patterns in relic radiation, by letting mathematics and observation argue until a hidden term revealed itself. That is one of the noblest things science can do, It can sit on a small world under a thin atmosphere, look up at ancient light, and infer that the vacuum of the universe is reshaping the future. In the end, dark energy is not just a topic in cosmology. It is a reminder of how reality behaves when it is allowed to be itself, not according to common sense, not according to comfort, but according to laws we are still uncovering. The universe is larger than our instincts, older than our myths, and stranger than its own visible light suggests. And somewhere in that strangeness, in the quiet between galaxies, may lie the reason everything ends the way it does. So the next time you look into the night sky, remember that the deepest mystery may not be the stars burning in the darkness. It may be the darkness itself, the vast seeming emptiness silently deciding how far, how fast, and for how long the universe can go. Thank you for being here, and if this journey pulled you in, I would love to know your answer in the comments. When you imagine the final future of the cosmos, what do you think it looks like?